wooden boxes are frequently found in a science laboratory. Inside each box is a very complicated instrument. What is it? Look at the congee soup in the beaker. You can't see anything special. Transfer a drop of it onto a glass slide and cover it with a cover slip. Look closely with the naked eye. There is nothing inside. Put the glass slide on the flat surface of the instrument and look through the window on top of the instrument. The congee soup is full of particles. They are starch particles. They are tiny objects. This instrument magnifies tiny objects to images of a visible size and is called a microscope. A microscope rests on a horseshoe-shaped base. This mirror is fitted at the center of the base. It serves to provide illumination by reflecting light from a lamp. On the base, there is an inclination joint, to which the C-shaped arm of the microscope is articulated. The upper end of the arm is joined to the body tube. On the upper part of the joint, there is a big knob called the coarse adjustment. A small turn of the coarse adjustment makes the body tube move up or down a long distance. The small knob below is the fine adjustment. You have to turn it round several times to move the body tube a short distance. The body tube is a steel barrel. The eyepiece is inserted into the upper end of the body tube. The eyepiece is in fact a metallic tube with a convex lens fitted at each end. A microscope is typically equipped with 3 eyepieces of different magnification. The lower end of the tube is connected to a dome-shaped revolving nosepiece. There are 3 holes for fitting in objectives of different magnification. The objective is also a metallic tube with a convex lens at each end. Below the objective is a flat stage. There is a big hole in the center for light rays to pass through and enter the objective. These mechanical parts next to the hole are used for fixing and moving glass slides, making it possible to place a specimen inside the hole for easy observation. Under the stage there is a condenser, which can be moved up and down. It is a very thick piece of glass, serving to converge light rays from the reflective mirror into a beam, which then enters the objective and illuminates what you're looking at. This part under the condenser is called the iris diaphragm. It is a set of black steel plates. By moving this control piece, you can adjust the size of the hole in the center so as to control the amount of light rays admitted into the objective. When observing specimens with the low power objective, it is advisable to use a smaller hole. This makes the light softer for better protection of the eye. When observing specimens with a high power objective, it is necessary to use a bigger hole to admit more light and make observation easier. Gently place the wooden box containing the microscope on the bench. Hold the arm of the microscope with one hand. Pull out the microscope and gently place it on the bench in front of you. eyepiece and the objective. If you wish to move a microscope, you should hold the arm with one hand and the base with the other to avoid dropping the microscope by accident. Remember to hold it with the mirror facing upwards. In this way, the mirror will not fall out. When you are about to use the microscope, you should clear the bench surface beforehand. Then, place the microscope in front of you with the arm facing you. Keep the microscope clear of the edge of the bench so as to prevent it from falling down by accident. Place your left hand firmly on the base and hold the arm with your right hand. Adjust the angle of the body tube by moving the arm backwards or forwards until the eyepiece is placed in front of your eyes and you are able to look through it comfortably. In this way, you can look into the microscope without much tension. Look into the eyepiece with one eye only. Meanwhile, turn the mirror to the left and the right until you can see a distinct image against a background of soft illumination. Don't turn the mirror towards the sun. Letting direct sunlight into the microscope will hurt your eye. If it is not possible to get a distinct image, clean the lenses on the eyepieces and objectives with a piece of lens paper. Never touch the lens with your fingers, as sweat or grease on the fingers will leave marks on the lens. These will cause molds and damage the lens. To observe a specimen under the microscope, put the glass slide on the stage and fix it with the clips. Move the slide until the area under the cover slip is over the central hole of the stage. Begin with the eyepiece and objective of the lowest magnification so as to view the whole specimen. The magnification of the microscope is calculated by multiplying the magnification of the eyepiece with that of the objective. It is 50 times. Watch the objective from the side. Turn the coarse adjustment so as to slowly move the objective to the lowest possible position. Try your best to prevent the objective from touching the cover slip so as to avoid breaking the slide. Look into the eyepiece again. With your thumb and index finger holding the upper and lower margins of the coarse adjustment respectively, move the thumb towards you and the index finger in the opposite direction. So as to gently move the tube upwards until you can see a distinct image inside. Then, turn the fine adjustment until you get a sharp image. To further magnify a portion of the specimen, you need to choose a combination of lenses of higher magnification. Now the microscope is capable of magnifying 400 times. If the specimen is very small, you will need to use the lenses of the highest magnification. Now the microscope is capable of magnifying 960 times. You should always turn the fine adjustment in such a direction as to move the objective away from the slide. Remember to keep both eyes open when you are looking into the eyepiece. If you are used to writing with the right hand, you should look into the eyepiece with your left eye and keep your right eye open to watch your right hand drawing or writing notes. A microscope should be kept inside its wooden box when it's not in use. The eyepieces and objectives should be removed, wrapped in lens paper and kept inside the plastic box with silica gel, so as to protect the lenses against damage by dust, grease and moulds. You can't see anything inside the pond water with the naked eye. Take out a drop of the water and place it on the centre of a glass slide. Place a cover slip with a dissecting needle. Lower the needle gently until the cover slip rests on the water. In this way, you can avoid trapping air bubbles in the water under the cover slip. Place the slide on the stage of the microscope and observe with a proper magnification. This small animal is a hydra. It looks like a tree. The cylindrical body has a number of tentacles which are used for catching food. This is a cluster of Vorticella. This tiny animal is a Halteria. Viewing with the naked eye, there is nothing significant in the water of the aquarium. Extract some water with a glass tubing. Transfer a drop of the water onto a glass slide. Seal with a cover slip and place it on the stage of a microscope for observation. This tiny animal is called a paramecium. It looks like a sole. It has many cilia on its body surface. This tiny animal is a Stylonychia. In the spring and summer days, the bays and coves of the SAR are occasionally attacked by red tides. A red tide is a disaster to fish culture farms. What exactly is a red tide? Let's observe a sample of red tide water with a microscope. There is a dense population of Gymnodinium, which is a kind of microscopic red algae. The body surface is covered with a coating bearing two grooves at right angles to each other. The sudden occurrence of Gymnodinium algae up to a concentration of over 1,000 pieces per milliliter rapidly depletes the seawater of oxygen or blocks the gills of the fish. As a result, all the fish in the affected waters die of suffocation. The microscopes for student use in the laboratory make use of light rays to go through thin, transparent specimens and lenses to form images. Hence, they cannot work on thick pieces and specimens made of non-transparent material. The problem is solved if a stereo microscope is used. A stereo microscope looks like a student microscope, but it works on a different principle. It forms images of objects reflecting light rays from the surface of the specimen and the stage. Its magnification is much lower. The stereo microscope is used for observation of large specimens and blood flow inside the frog web. 300 to 400 years ago, Europe was savaged by a large number of infectious diseases. Doctors could not cure the patients because they were unable to identify the disease-causing agents with the naked eye. In the late 17th century, Anton van Leeuwenhoek in Holland observed the matter trapped in gaps between teeth with his homemade microscope. He found many tube-like objects of various lengths and made detailed drawings of these things. He called them microorganisms. In the late 19th century, Louis Pasteur in France observed various materials through modern microscopes. He identified many microorganisms of similar shapes in bad wines, sour milk, and the body matter of sick domestic animals. Louis Pasteur named them bacteria. Meanwhile, Dr. Robert Koch in Germany observed body matter from patients through microscopes. He confirmed that bacteria were disease-causing agents. An example of bacteria is E. coli, which lives in the human large intestine. E. coli bacteria are discharged in feces. When brought to sea by the drainage system, the bacteria survive and breed in the seawater. Scientists use the concentration level of E. coli in seawater as an indicator of the level of pollution caused by domestic sewage. The large mass of E. coli bacteria on the human skin may contaminate food. If the food is consumed without cooking, disease caused by the bacteria can follow, giving rise to food poisoning. Whenever food poisoning occurs, health department officials collect specimens of the food and of the excreta of the victims for culture tests. If the form of the bacterial colonies on the agar plate look like the typical E. coli colonies, a sample of the colonies will be taken away, stained, and placed on the stage of the microscope for observation at high magnification to confirm the identity of the bacteria. In this way, scientists have successfully identified many kinds of bacteria which have been confirmed as disease-causing agents. The microscopes used in hospitals and schools make use of light for illumination. Hence, they are commonly known as light microscopes. Limited by the physical nature of light waves, the highest possible magnification of light microscopes is 1,500 times. Advances in electrical machinery and electronic technology in the early 20th century led to the invention of electron microscopes with magnification up to 500,000 times. Modern computer technology enables scientists to derive well-contrasted and colored pictures from images generated by electron microscopes. An electron microscope is a steel tower with an electron gun on top. Below it is a small window for insertion of specimens. On the bottom is the electromagnetic chamber. The electron gun emits a beam of electrons which penetrate the specimen. Then, the electron beam travels into the electromagnetic chamber where it is much magnified. The signals are received and processed by the computer, which converts them into a picture on the monitor. In this way, each tiny fuzzy dot of E. coli bacteria under the light microscope is magnified by the electron microscope into a large picture with distinct details. The electron microscope reveals a bizarre world beyond our imagination. For example, the compound eye of an insect looks like a beehive. This fancy object is in fact a much magnified gunshot residue. The electron microscope enables us to observe things in a brave submicroscopic world. It enables us to manufacture microelectronic appliances. Moreover, it enables us to develop new ways to combat genetic disorders and many deadly diseases.